Hello everyone, I'm Tianyu Zhu from University of Connecticut. It's my great honor to be here and give a presentation on the title of Detection and Correction of Buffer Occupancy Data Error in Two-Machine Bernoulli serial lines. The outline is as follows. First part, I will introduce the background of our research. The second part is about the problem formulation. The third part covers the algorithm and results for error detection in two machine lines. And then I will show our algorithm and results for error correction. Finally, conclusions and future work will be given. Within Industry 4.0, Smart Factory is a focus area aimed at deploying sensing and controlling to the production equipment and the overall system to achieve the goal of automation. To achieve Smart Factory, it's well recognized that one of the important components is continuous monitoring of the production status in every step of the manufacturing system at hand. In the past few decades, advances in sensing, computing, and industry control technologies have greatly popularized their deployment on the factory floor to facilitate the production activity monitoring, coordination, and decision-making. This has resulted in more production-related data being generated and collected in a more affordable and accessible manner than in the past. On the other hand, development of analytics tools to digest these factory floor data and extract useful information for production decision-making and control has been lagging behind. Moreover, due to the technology limitations of the sensors and the noisy environment in the manufacturing facilities, it's quite common that the raw data collected from the factory floor contain errors and often must go through a time-consuming, labor-intensive data cleaning process before they are ready to be fed to any tools. This is one of the main challenges and concerns about the use of factory floor production data in practice. To address this challenge, we intend to develop methods for automated detection and correction of such errors. Consider a production line with two workstations, also called machines, in the following discussions, and one in-process buffer. Workstations follow Bernoulli reliability model, and the buffer capacity is n. We assume that a sensor is placed at the buffer to monitor its occupancy data, Hn, the number of parts in buffer at the end of time slot n, and Hn tilde, the number of parts in buffer during time slot n. In practice, this can be realized using various sensing technologies, such as photoelectric sensors, wave sensors, camera sensors. In future work, we will study the cases where other system information is available. Based on Hn tilde and Hn, it's possible to deduce the parts flow on the workstations. Let Yn denote the number of parts processed by workstation during time slot n. Then we can get this function. Obviously, Yn should be 0 or 1. In addition, we can also calculate the performance metrics of the production system based on the buffer occupancy, Hn tilde and Hn. The average production rate of the system and the average working process of buffer can be calculated using the following functions. Due to the technology limitation of the sensors and the noise in a manufacturing environment, the measured data may contain errors, leading to the deviations from the true quantities being measured. In our paper, to quantify the effects of the data error and develop methods to alleviate such effects, let Hmn tilde and Hmn denote the measured buffer occupancy data at time slot n, and assume that either one has a probability of Q to differ from its corresponding true value, Hn tilde or Hn. In addition, assume these functions are satisfied. Thus, under these assumptions, when a measurement error occurs, the sensor will randomly return an arbitrary number other than the true value within the feasible range from 0 to n. This error model is appropriate when the measurement is subject to a noisy environment. For example, effects of variable lighting condition on a camera sensor. It also can be used when no knowledge about the exact error model is available. Other error models will be considered in the future work. Based on the measured buffer occupancy data, the system performance metrics are estimated. Clearly, the errors in the raw data may propagate to the performance metric estimates. Using these estimates as a basis for production control and decision making may affect the operation efficiency of the system. Therefore, in our paper, the following problems are addressed. Data error detection. Detect the errors in the buffer occupancy time series data. Data error correction. Reconstruct the buffer occupancy time series data by correcting the errors in the data. Clearly, similar to the functions in the previous slides, the machine processing status can be estimated based on the buffer occupancy data. Thus, to determine if an error has occurred in the data, one can identify whether the observed YMN are within their feasible range. This is our error detection criterion. Clearly, this criterion relies on the relationship of the buffer occupancy data. When it reports an error, it's certain that an error has actually occurred among the data entries flagged by the EDC. However, this criterion cannot identify the exact data entry that has error. Therefore, if YM1N belongs to this set, then both HMN and HMN tilde are flagged as potential error data entries. It is also similar to YM2N. On the other hand, some errors may go undetected based on the criterion. To evaluate the error detection performance of the EDC under the noise model, we define alpha, beta, and gamma. A total of 2,000 pairs of machine efficiency combinations are generated with P1 and P2, randomly and independently selected from this range. For each machine efficiency combination, we simulate the system for t equals to 20,000 times source, with n belongs to that set, to obtain the true buffer occupancy time series data, Hn and Hn tilde. Then the noise model is applied to each set of Hn and Hn tilde to create the measured data set. Finally, EDC is applied to each measured dataset, and metrics alpha, beta, gamma are calculated. As one can see, the EDC performs better on the noise model when buffer capacity is larger. This is because the larger range of error data leads to higher probability that YMIN may go out of its feasible set and get detected by the EDC. Note that while EDC would fail to detect 10 to 30% of errors on average, these undetected errors only correspond to about no more than 5% of the entire dataset. On the other hand, as shows, over half of the data entries flagged by the EDC are not actual error entries. Since Hn and Hn tilde are time series data. Losing the detected error data points not only breaks the long time series into short fragments, but also lead to the lost information. Due to these issues, it's important to correct the data entries and repair the dataset. Thus, we propose a data block-based approach that can effectively and efficiently identify and correct the errors in the buffer occupancy data. To locate and correct the errors in the buffer occupancy data, note that the measure dataset can be expressed as a table, with each row n representing the measure data of time slot n. For this dataset, define data block ij, denoted as dbij, as a subset of the data starting from row I and ending at row j, where rows I and j are referred to as the starting and ending boundary rows of dbij. The starting and ending boundary rows should satisfy these constraints. The starting and ending boundary rows thus created will result in a number of data blocks cover a certain portion of the entire dataset. Next, the data blocks created above will be treated independently by the data error correction algorithm. This is the basic logic of our algorithm. First, convert the raw dataset Hn to Yn, and identify the starting and ending boundary rows, and then separate the data table into blocks based on the boundary rows. After that, enumerate all valid combinations of Yn. Choose one that introduces minimal modifications to the original measured data. Finally, repeat the step 2 for every block. To evaluate the performance of our algorithm under the noise model, 502 machine Bernoulli lines are simulated with machine efficiency P1 and P2 randomly selected from this range. Time slot T equals to 1000. Buffer capacity N equals to 5. For each line, we can use the functions in the previous slides to calculate the true performance metrics PRT and WIPT of the system and calculate the relative errors estimated by the measured data before and after the algorithm is applied. As one can see, correcting the errors in the buffer occupancy data using the algorithm can reduce the performance metrics estimation errors by over 75% for both PR and WIP. In addition, to evaluate the correction performance of our algorithm, define PW and PW star. PW star consists of PCW, PWW, and PU, the three parts. While the ECA cannot completely recover the true buffer occupancy data, the inconsistency is reduced by about 60%, and the output data is guaranteed to possess data integrity. In our paper, we studied the detection and correction of errors in the buffer occupancy time series data in two machine Bernoulli serial lines that are subject to measurement noises. Effective algorithms are developed to detect and correct data errors. Numerical experiments show that the algorithm can correct the majority of errors and restore data integrity. Future work includes extending the work to multi-machine Bernoulli lines, other machine reliability models, noise models, and system structures, and testing the theoretical results in the lab environment and true industry settings. That's all for my presentation. Thank you.